Hey everyone, welcome to this explainer. I am so glad you're tuning in today. If you're the kind of focused learner who absolutely loves taking a complex, maybe even slightly intimidating engineering problem and breaking it down into super clear, deeply satisfying steps, well, you are in the exact right place. Today, we're going to completely decipher the math behind a three-phase induction motor. We're taking a piece of raw source material, we're decoding the variables, and we're going to walk away with a crystal clear understanding of how the whole shebang works. Let's get right into it.
All right, let's just jump right in. What we're looking at here is a classic, handwritten engineering problem focused on a three-phase induction motor. And it even has this really neat little diagram showing the three-phase supply lines. The problem itself reads, a three-phase induction motor has a synchronous speed of 1,000 RPM and a slip of 5%. It then asks us to find three very specific outputs. Honestly, I want you to treat this thing like a locked box. It looks sealed tight right now, but embedded right there in the text are the exact keys we're going to need to pry it open.
So, here's our game plan. First, we'll define our given variables. Second, we'll calculate the rotor speed. Third, we'll find that rotor frequency. Fourth, we'll determine the mechanical power developed. And finally, we'll wrap it all up with the final output.
All right, step one, defining the given variables.
You gotta love how neatly the original author laid this out. We've taken their given section and dropped it into a quick table here. We essentially have four main clues to work with. First up, synchronous speed. That's ns, sitting at a solid 1,000 RPM. Next, we've got our slip, represented by a lowercase s, which is 5%. But remember, for the math, we're going to convert that right into a decimal, making it 0.05. Third, the rotor input power, or P2, is 20 kilowatts. And last but not least, our supply frequency, F, is 50 hertz. Go ahead and lock these four numbers in your brain because they are literally the keys we'll use to crack the rest of this problem.
Moving right along to step 2, calculating the rotor speed.
To figure out the actual rotor speed, we'll just call that n, we're going to need a specific formula. And here it is. N equals ns times the quantity of 1 minus s. It's actually a pretty elegant little equation, right? Our big unknown, n, depends entirely on just two things we already know, the synchronous speed and the slip.
Okay, let's peel this onion layer by layer so we don't get overwhelmed. Step 1 is just simple plug and chug. We grab our synchronous speed, ns, which was 1,000, and our slip, s, which is 0.05, and we drop them right into the formula. That gives us n equals 1,000 times the quantity of 1 minus 0.05. For step 2, we just clean up the math inside those parentheses. 1 minus 0.05 leaves us with 0.95. So the whole calculation simply boils down to 1,000 multiplied by 0.95.
And boom, there it is, 950 RPM. That is our calculated rotor speed. First major victory in the bag. And honestly, this perfectly highlights a core rule of induction motors. Your physical rotor speed is basically always going to be just a little bit less than your synchronous speed. That 5% slip literally drags the 1,000 RPM theoretical max down to a real-world operating speed of 950 revolutions per minute.
All right, now that we've got our speed, let's jump into step 3, finding the rotor frequency.
For this one, we need a new forensic tool, and honestly, it doesn't get much simpler than this formula. Rotor frequency, which we write as Fr, is just equal to the slip, S, multiplied by the supply frequency, F. It directly pairs up those two given variables.
Let's keep the momentum rolling and knock out this calculation. Step 1, we plug in our data. Our slip, S, is 0.05. Our supply frequency, F, is 50. So, Fr equals 0.05 times 50. Step 2, we just multiply them together.
And there you have it, 2.5 hertz. Punch that in as answer number 2. But hold on, let's take a second to really appreciate what this actually means in the real world. The initial electrical supply is pulsing incredibly fast, right at 50 hertz. But because of that 5% slip we identified earlier, the frequency actually experienced over at the rotor drops all the way down to a mere 2.5 hertz. It is a massive physical transformation, and it's driven entirely by that tiny little slip percentage. Pretty wild, right?
Okay, on to the really fun stuff. Step 4, determining mechanical power.
Here's our final formula for this explainer. The mechanical power developed, let's call it PM, is calculated by taking the quantity of 1 minus the slip and multiplying all of that by P2, which is our rotor input power. Once again, we're just taking those basic givens and combining them to reveal our final unknown.
Let's break this math down one last time. Step 1,
Insert the slip, so 0.05, and the P2 input power, which the problem told us was 20 kilowatts. That gives us PM equals the quantity of 1 minus 0.05 multiplied by 20. Step 2, we clean up the parentheses again, which leaves us with 0.95. Then we simply multiply that 0.95 by our 20 kilowatts of input power. And this right here demonstrates exactly how theoretical math translates into actual real-world mechanical power.
19 kilowatts. Man, what a deeply satisfying number to land on. Think about it. We pumped 20 kilowatts of electrical input power into this rotor. But the actual physical mechanical power we developed is 19 kilowatts. You naturally lose a tiny fraction in that conversion process, and it's dictated entirely by that 1 minus s mathematical reality.
Which brings us to the finish line. Section 5, the final output.
Taking a page straight out of our original source materials answers block, look at what we've actually accomplished here today. We started with just a dense little paragraph of text and 4 given clues, and we have totally decoded this motor's operating parameters. Our rotor speed, 950 RPM. Our rotor frequency, 2.5 Hertz, and the mechanical power developed, 19 kilowatts. We literally took abstract engineering math and mapped it directly onto the physical reality of how this machine operates. But I want to leave you with one final, fascinating thought to chew on today. Throughout all of these calculations, there was one tiny metric dictating everything, that 5% slip. It lowered our speed, it absolutely tanked our frequency, and it capped the mechanical power. So if a mere 5% slip shapes the entire power output this drastically, just imagine how perfectly tuned and constantly monitored our massive industrial motors out in the real world must be to keep global infrastructure running smoothly. It's just a phenomenal application of physics. Thanks so much for joining me to crack this code today, and as always, keep learning.